friends, up to this we have completed the exercise 2.1, 2.2. Now we'll start the next exercise 2.3. That's the Rolle's theorem and the Lagrange mean value theorem. We have completed the exercise 2.1 and 2.2. In that exercise we have seen that how to find out the equation of the tangent and normal to the given curve at that point, and the velocity, acceleration and the jerk depending the problems. And in the next exercise, we have seen to find out the approximate value of the given function at that point. And now this will start the next and very interesting topics, that is the Rolle's theorem and the Lagrange mean value theorem. Rolle's theorem. Or Rolle's lemma. If a real valued function f is continuous on closed interval ab, and differentiable on the open interval ab, and f of a is equals to f of b, there exists at least one c in the open interval in the open interval ab such that f dash of c is equals to 0. Rolle's theorem essentially states that any real valued differentiable function that attains equal values at two distinct points on it must have at least one stationary point somewhere in between these 2 points, in between them, that is a point where the first derivative is 0. That is, the slope of the tangent line to the graph of the function, that is slope of that line, it is a 0. And when the slope of any line is 0, when it is a parallel to x-axis. Now see this here. Now in figure these are the two curves, and this is the value of the function at a, that is f of a, at b, and there is a point c. It is a tangent to the given curve and its a slope is 0. In the same way, here is also the curve. These are the 2 points a and b. Their values f of a, f of b, and here is a f of c. It's a derivative at this point, that is equals to 0. Means what? Slope of the curve at that point is 0. Now see this again here. Geometrical significance. Means the meaning of this, let f of x, what is the geometrical meaning for this? Let f of x be a real valued function defined on closed interval a b and it is a continuous on closed interval a b. This means that we can draw the graph f of x between the values x is equals to a and x is equals to b. Also, f of x is differentiable on open interval which means the graph of f of x has a tangent at each point of AB Now the existence of a real number small c belongs to AB such that f dash of c is equals to 0. Shows that the tangent to the curve at x is equals to c has a slope 0. See this, the tangent which is parallel to x-axis, that is tangent is parallel to x-axis since f of a is equals to f of b. This condition must be satisfied. We'll see the illustrative examples. check whether conditions of Rolle's theorem are satisfied by the following. First, f of x is equals to 2x cubed minus 5x square plus 3x plus 2, where x belongs to closed interval 0, 3 upon 2. Now we have given that f of x is equals to 2x cubed minus 5x square plus 3x plus 2. This is 1. Now this is the polynomial function. It means that it contains the powers of the x which are the whole number. F of x is a polynomial function which is a continuous on closed interval 0, 3 by 2, and it is a differentiable on open interval 0, 3 by 2. Whenever there is a polynomial function, that function is always continuous on that interval. Let first is a is equals to 0 and b is equals to 3 by 2. Now find out their values. For x is equals to a, that is f of a is equals to f of 0, that is 2 into 0 square minus 5 into 0 plus 3 into 0 plus 2 . For x is equals to b, that is equals to 3 by 2. From 1 we get f of b is equals to 3 by 2. 2 into 3 by 2 cube minus 5 into 3 by 2 square plus 3 into 3 by 2 plus 2. That is 54 upon 8 minus 45 upon 4 plus 9 by 2 plus 2. And after simplification, you will get that is a 2. So here f of a is equals to f of b, that is both values are equal. The value of a is 2 and value of b is also 2. Therefore f of a is equals to f of b, that is f of 0 is equals to f of 3 by 2 is equals to 2. Hence the condition of Rolle's theorem are satisfied. And then there is the point C, find the value of that point C is also. Second, f of x is equals to x square minus 2x plus 3. X belongs to closed interval 1 to 4. Now again the given function f of x, it is a polynomial, it's continuous on the closed interval 1 to 4. Which is continuous on closed interval 1 to 4, and it is differentiable on open interval 1 to 4. That a is equals to 1 and b is equals to 4. For a is equals to 1, that is x is equals to 1, from 1 we get f of a is equals to f of 1 is equals to its value, and its value is comes to 2. 1 square minus 2 into 1 plus 3, that is equals to 2. And for x is equals to b is equals to 4, f of b is equals to f of 4, 4 square minus 4 into 2 plus 3, that is equals to 11. So f of a is not equals to f of b, that is f of 1 is not equals to f of 4, and therefore the conditions of the Rhodes theorem is not satisfied here. Hence the condition of Rhodes theorem is not satisfied. Example number 2. Verify Rolle's theorem for the function f of x is equals to x square minus 4x plus 10 on closed interval 0 to 4. Now the given function f of x is equals to x square minus 4x plus 10 f of x is a polynomial function, is a polynomial which is continuous on the closed interval 0 to 4, and it is a differentiable on open interval 0 to 4. This is the fixed dialog. That's you have to write. Now we'll find out the value. Let a is equals to 0 and b is equals to 4. Now if for x is equals to a is equals to 0, from 1 it's a value, and its value will be 10. X is replaced by 0. 0 square minus 4 into 0 plus 10, that is equals to 10. For x is equals to b is equals to 4. From 1 we get f of b is equals to f of 4 is equals to 4 square minus 4 into 4 plus 10, that is equals to 10. That's all conditions of the Rolle's theorem is satisfied. Now find the value of the c. all the conditions of the Rolle's theorems are satisfied. To get the value of C, we should have f dash of C is equals to 0. This point C lies between 0 to 4 and its a derivative at that point is equals to 0, f dash of C. Now differentiate the given function, its a derivative is a 2x minus 4 and that's equals to 0. That is a 2 in bracket C minus 2 therefore C is equals to 2. C is equals to 2 which belongs to open interval 0 to 4. Thus the Rolle's theorem is verified. That is C lies between 0 to 4. Given an interval closed interval AB that satisfies hypothesis of Rolle's theorem, for the function f of x is equals to x cube minus 2x square plus 3, it is known that a is equals to 0. Find the value of b. Now, the given function satisfies the conditions of the Rolle's theorem. That is f of a is equals to f of b. If we have the value of a is 0, we can find out the value of b also. Now see this here, f of x is equals to x cube minus 2x square plus 3. Therefore, it's written as like this: g of x is equals to x cube minus 2x square, f of x is equals to g of x plus 3. Therefore, we can write that is for x is equals to 2, it's obvious that the f of x is continuous everywhere and differentiable of a cubical polynomial. Consequently, it satisfies all the conditions of Rolle's theorem. and here the value of d is 2. Simple way, you can find out in different way also. Verify the Rolle's theorem. For the function f of x is equals to e raised to x in bracket sin x minus cos x on pi by 4, closed interval pi by 4 and phi pi by 4. Given that f of x is equals to e raised to x in bracket sin x minus cos x, we know that e raised to x, sin x, cos x, these are the continuous on their domains, and therefore the given function is a continuous and differentiable on closed interval pi by 4 to phi pi by 4 and differentiable on open interval pi by 4, phi pi by 4 respectively. Now we'll find out their values. At a is equals to pi by 4 and b is equals to phi pi by 4. For x is equals to a, that is equals to pi by 4. And this is the board question also asked in the CET exam. F of a is equals to f of pi by 4, that is e raised to pi by 4 in bracket sin of pi by 4 minus cos of pi by 4. That is 1 by root 2 minus 1 by root 2, and overall you will get its a value that is equals to 0. For x is equals to b, that is 5 pi by 4. From 1 we get f of b is equals to e raised to 5 pi by 4 in bracket sin of 5 pi by 4 minus cos of 5 pi by 4, and it's a value 5 pi by 4. Its value is minus 1 upon root 2 plus 1 upon root 2. Both of them there. F of b is equals to f of a, that is equals to 0. All conditions of Rolle's theorem are satisfied. To get the values of C, that we should have the f dash of C is equals to 0 for some C belongs to pi by 4 and 5 pi by 4. Now differentiate one with respect to x. F dash of x is equals to e raised to x in bracket cos x plus sin x plus sin x minus cos x into again into the derivative of e raised to x, which is e raised to x. If you simplify it, then you will get f dash of x is equals to 2 e raised to x into sin x. For x is equals to c, f dash of c is equals to 0. That is a 2 e raised to c sin c is equals to 0. As e raised to c is not equals to 0. For any value which belongs, that is c belongs to R, each value 0 येऊ शकत नाही. Therefore, sin of c is equals to 0. Then, for what values of the sin c is 0? Then it is 0 plus or minus pi plus or minus 2 pi plus or minus 3 pi. It's a clearly seen that is printing mistake. That is, the pi belongs to pi by 4 and 5 pi by 4. Therefore, c is equals to pi. Thus, the Rolle's theorem is verified. Lagrange mean value theorem. This is again interesting. If a real valued function f is continuous on closed interval ab and differentiable on open interval ab, then there exists at least one c in the open interval ab such that f dash of c is equals to f of b minus f of a upon b minus a. Lagrange mean value theorem states that for any real valued differentiable function which is continuous at two end points, there is at least one point the tangent is parallel to the second through its end points. This is important. The tangent is parallel to the second through its end points. Now, this is important. These are the points for this given curve. A and B are the 2 points. We join this as the second. there is at least one point, and that point is C, small c. At this point, this tangent is parallel to this secant AB, and this is the difference. Now, a small difference between that is a Rolle's theorem and the Lagrange mean value theorem. These are the two different statements. In this case, this tangent is a parallel to this secant. But in that case, that is equals to 0. Slope of that tangent was 0 in Rolle's theorem. And here the slope is not 0. Now the geometrical significance. Draw the curve y is equals to f of x and take the endpoint a, small a f of a, and b f of b on the curve, then slope of the chord AB is equals to f of b minus f of a upon b minus a. Since by statements of Lagrange mean value, Lagrange mean value theorem, f dash of c is equals to f of b minus f of a upon b minus a. That is, f dash of c is equals to the slope of the chord. F dash of c is equals to the slope of the chord AB. This shows that the tangent to the curve y is equals to f of x at the point x is equals to c is a parallel to the chord AB. Now verify the Lagrange mean value theorem. For the function f of x is equals to in root of x plus 4. On the interval 0 to 5. Given that f of x is equals to root of x plus 4, the function f of x is a continuous on the closed interval 0 to 5 and differentiable on the open interval 0 to 5, so that the LMVT is applicable to the function. Now differentiate this with respect to x. F dash of x is equals to 1 upon 2 times in root of x plus 4. Now for a is equals to 0, that is, let a is equals to 0 and b is equals to 5. We'll find out their values. A is equals to, that is f of 0, that is 2. And find out b, that is f of b, that is f of 5 in root of 5 plus 4, that is equals to 3. Let small c belongs to the open interval 0 to 5 such that f dash of c is equals to f of b minus f of a upon b minus a. That is 1 upon 2 in root of c plus 4, that is a 3 minus 2 upon 5 minus 0, that is 1 upon 5. Now take their reciprocal and simplify. Root of c plus 4 is equals to 5 upon 2. Squaring on both sides, then you will get c plus 4 is equals to 25 by 4, and simplify this. That is, you will get 9 by 4, and this 9 by 4, it belongs to 0 to 5. That is 2 point something which belongs to 0 to 5, and thus the Lagrange mean value theorem is verified. Next, verify the Lagrange mean value theorem for the function f of x is equals to x plus 1 upon x on the closed interval 1 to 3. Given that f of x is equals to x plus 1 upon x, the function f of x is continuous on closed interval 1 to 3, and differentiable on the open interval 1 to 3, so that the LMVT is applicable to the function. Now differentiate the first with respect to x. F dash of x is equals to 1 minus 1 upon x square next is let a is equals to 1, b is equals to 3. Their values, f of a is equals to f of 1 that is equals to 1 plus 1 2, f of b is equals to 3, f of 3 is equals to 3 plus 1 upon 3, that is a 10 upon 3. Now this small c belongs to open interval 1 to 3 such that f dash of c is equals to f of b minus f of a upon b minus a, that is 1 minus 1 upon c square is equals to 10 upon 3 minus 2 upon 3 minus 1. And if we simplify it, 1 minus 1 upon c square is equals to 4 upon 3 upon 2, and that is equals to 2 upon 3. 1 minus 1 upon c square is equals to 2 upon 3. That is 1 minus 2 by 3 is equals to 1 upon c square, and that is equals to c is equals to root 3 plus or minus root 3. We take its value as a plus and belongs to the open interval 1 to 3. And the value of c minus root 3 does not belong to open interval. And in this way, we have completed all the solved and explanations. Now we'll start the exercise 2.3. Check the validity of Rolle's theorem for the following functions. Now in first two questions I had only checked, and afterward I find out the value of the c also. Check the validity of Rolle's theorem for the following function. F of x is equals to x square minus 4x plus 3. X belongs to closed interval 1 to 3. The function f given as f of x is equals to x square minus 4x plus 3 is a polynomial function. Hence, it is a continuous on closed interval 1 to 3. And differentiable on open interval 1 to 3. Now first find out the value f of 1. 1 square minus 4 into 1, that is 4 minus 1, that is equal to 0. F of 3. 3 square minus 4 into 3 into plus 3, and that's value is 0. And therefore the conditions of the Rolle's theorem are satisfied here. F of 1 is equals to f of 3. Thus the function f satisfies all the conditions of the Rolle's theorem. Second, f of x is equals to e raised to minus x into sin x, where x belongs to open interval 0 to pi. The function e raised to minus x and the sin of x are continuous, and differentiable on their domains, that is 0 to pi. Now their values. F of x is equals to e raised to minus x sin x is a continuous on open interval 0 to pi and differentiable on closed interval 0 to pi. F of 0 is equals to e raised to 0 sin 0, that is equals to 0. F of pi, that is e raised to minus pi sin pi, that is e raised to minus pi and sin of pi is 0, and overall you are getting the 0. F of 0 is equals to f of pi. Thus, the function f satisfies all the conditions. Now next, for these two problems, we will find out the value of c also. Thus, the function f satisfies all the conditions of Rhodes theorem. After the problem C, that is a 2x square minus 5x plus 3. X belongs to closed interval 1 to 3. The function f given as f of x is equals to 2x square minus 5x plus 3 is polynomial function hence it is a continuous on closed interval 1 to 3 and differentiable on open interval 1 to 3. Now we'll find out their values. F of 1, that is 0, f of 3, that is equals to 6 and it is not equals to 0. Therefore, f of 1 is not equals to f of 3 and hence it is not valid. The function f does not satisfy all the conditions of Rolle's theorem. Fourth one, f of x is equals to sin x minus cos x plus 3. X belongs to closed interval 0 to 2 pi. The function sin x, cos x and 3 are continuous and differentiable on their domains. F of x is equals to sin x minus cos x plus 3 is continuous on 0 to 2 pi and differentiable on open interval 0 to 2 pi. Therefore, their values f of 0, sin 0 cos 0 plus 3, sin 0 is 0, cos 0 is 1, and overall you are getting that is f of 0 is 2, f of 2 pi, that is the sine of 2 pi is 0, cos of 2 pi is 1, and 3. Overall you are getting the f of 2 pi, that is 2. Therefore, f of 0 is equals to f of 2 pi. Thus, the function f satisfies all the conditions of for the Rhodes theorem. Now there exists, we will find out the value of the C also. There exists the C belongs to 0 to 2 pi such that f dash of C is equals to 0. Now here f of x is equals to sin x minus cos x plus 3, their derivatives. That is the cos x plus sin x f dash of C, that is the cos C plus sin C, that is f dash of C is equals to 0 gives cos C minus sin C now what should be the value of C? That is sin C plus cos C, that is equals to 0. Therefore, the value of the C is 3 pi by 4 and 7 pi by 4. If we take these values from the trigonometry, if we take the value of the C is 3 pi by 4. Now the sine of, if we take here, that is sin C 3 pi by 4 and 7 pi by 4. Therefore, for these values, for the problem number first, we can also find out the value of the C. Now C belongs to 1, 2, 3 such that now in the previous problem, out of these two values, we take the 7 pi by 4 here. And that's why we will get its a value as a 0. Now next is f of x is equals to e raised to minus x into sin x. X belongs to 0 to pi. It's a derivative by using the product rule. E raised to minus x into cos x, derivative of sin x, plus derivative of e raised to minus x minus e raised to minus x into sin x. Take e raised to minus x as form. Then you will get cos of x minus sin x. F dash of C, that is e raised to minus c cos C minus sin C, that is equals to 0. E raised to minus c is not 0. Then what will be the 0? Cos C minus sin C, that will be the 0. Therefore, cos C minus sin C, that is equals to 0. Therefore, sin C is equals to cos C, and at what values they will be equal, that is C is equals to pi by 4. And it belongs to closed interval 0 to pi. Yes. This is the value of the C for the problem number 2. For the problem number 1 and 2, we have not find out. And in this way, we have completed the first part of this exercise. Now we will continue in the next video. Till then, goodbye.